All right, 2-1A is all on proportional relationships. So chapter 2 is a huge stepping stone into algebra for next year. So 2-1A through 2-1C are going to be a lot of review for you guys, but then we're going to move into things called slope-intercept form and finding the slope and writing equations in slope-intercept form. So these are a really big stepping stone going forward. All right, so it says here, in the previous chapter, you wrote equations with one variable to describe many situations mathematically. In this chapter, you will learn how to write an equation that has two variables to represent a situation. In addition to writing equations, you can represent real-world situations in other ways. In 6th and 7th grade, you studied proportional relationships and represented these relationships in various ways. The problems below will help you review how ratio and proportion can help you relate and represent mathematical quantities from a given situation. Okay, it says Julia's picking teammates for flag football. She picks 3 girls for every boy. So complete the table below to show the relationship of boys to girls on Julie's team. So for every 3 girls, she picks 1 boy. So 1 boy, she has 3 girls. There's 2 boys, 6 girls. 3 boys, there will be 9 girls. And 4 boys, there will be 12 girls. So in this situation, they say graph the girl to boy relationship for Julie's team with boys on the x-axis. So a friendly reminder, this is your x, and girls on the y. Okay, so I can put an X above boys, a Y above girls. Let's go ahead and label this. So we have boys down here on the X, girls on the Y. And as I go through and label, I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I can do the same thing here. Maybe I go up by twos. 2s, 4, 6, 8, 10, 12. All right, so if I have 1 boy, I have 3 girls. If I have 2 boys, I'm going to have 6 girls on the team. 3 was 9. 4 was 12. Okay, it says find the ratio of the girls to boys for several different ordered pairs in this table. Okay, well, girls to boys. So if I have 6 girls, that means I'll have 2 boys. If I have 3 girls, I have 1 boy. If I have 9 girls, I'll have 3. And if I have 12 girls, I'll have 4 boys. Fill in the tables below to show the relationship between girls and boys on Julie's team. Okay, well, for every girl, I multiply the number of boys times 3. All right, in other words, my y, the outcome, depends on the number of boys times 3. Okay, that will lead to my y. And we're going to be talking in this chapter about how I can connect all my points and have them go to the origin, 0, 0, and this forms a proportion. Use the equation and graph to determine how many boys will be on the team if she chooses 10 boys on the team. Okay, or how many girls would be on the team. So I need to plug 10 in for boys. So 3 times 10, well, how many boys would be on the team? 30. Or girls, sorry, 30 girls. Use the equation and graph to determine how many boys are on the team if we have 18 girls. Well, that would mean I'm plugging 18 in over here. I get 18 equals 3 times b, or 3b. How could I solve for b? Divide both sides by 3. So the number of boys on my team would have to be 6. So in this chapter, we're going to be doing a few things. We'll be filling out tables. We'll be graphing, labeling our x and y axis. We'll be solving for equations and setting up equations, and then plugging numbers in for real-world situations. In the previous example, the 2 quantities of interest are proportional relationships. Recall when 2 things are proportionally related, the ratio of each y value to its corresponding x is constant. This constant is called the constant of proportionality, or the proportional constant. Okay, the ratio related to the number of girls to boys was 3 up above. This is a proportional constant for this relationship. Okay, so it says, we're going to come down here to number 2. Carmen is making homemade root beer for an upcoming charity fundraiser. The number of pounds of dry ice to the pounds of root beer extract are proportionally related. if Carmen uses 12 pounds of dry ice, she will need, so I'm going to put an I above that so we remember that, she will need 8 pounds of root beer extract. So I'm going to do RBE for root beer extract, just so we remember that. Write a ratio or proportional constant that relates the number of pounds of dry ice to the number of root beer. So we know it's going to be 12 to 8. All right, write a ratio proportional constant that relates the number of ounces of root beer to the number of dry ice. This one's a little different. So here it says that relates the number of dry ice, so ice to root beer, right? But when I read this one first, they want me to put root beer first to dry ice. So I'm going to flip it. This one's going to be 8 to 12. It says, notice the proportional constant depends on what you define as your x and your y. So it says, complete the table below to show the relationship between the number of ounces of root beer extract, is your x, the number of pounds of dry ice. So we know to have 8 ounces of root beer extract, we need 12 pounds of dry ice. Okay, well, how would I get from 12 to 6? I would divide by 2. So 8 divided by 2 gives me 4. Okay, well now my question is, how can I get from 12 to 1.5? If you do this in a calculator, 12 divided by 1.5, you end up getting 8. So I know I'm dividing by 8 here, which means 8 divided by 8 gives me 1. So for every 1 ounce of root beer extract, I need 1.5 pounds of dry ice. So if I do this correctly, that means 8 times 1.5 should give me 12. Sure does. That means 4 times 1.5 should give me 6. It does. Well, then what's 3 times 1.5? If she needs 3 ounces of root beer extract, if I multiply that by 1.5, I end up getting 4.5. And 2 times 1.5 gives me 3. Well, if she doesn't make any root beer extract, she doesn't need any ice. So that would be 0, 0. So 0, 0. Let's go ahead and label our x and y intercepts. Okay, so my x is going to be root beer. Okay, so I'm going to go ahead and label this. So I'd have 1, 2, 3, 4, 5, 6, 7, and 8. And then my pounds of dry ice. Oh, that's bad. Sorry. Pound of ice. Go ahead and label it. I'm going to go up by 2s. 2, 4, 6, 8, 10, 12, 14. Now for this, it's really important that you just stay consistent in what you're going up on your y-axis by. So I'm going to say 1, 3.5. 2 was 3. 3 was 4.5. 4 was 6. 8, they skipped a couple numbers there, is 12. So when I graph it, my graph looks like this. Notice how it goes to the origin at 0, 0. So what is the proportional constant of this relationship? 1.5. And the reason why is because for every 1 ounce of root beer extract, I need 1.5 pounds of dry ice. So write an equation that shows the relationship between the number of ounces of root beer, notice how that's my x, and the pounds of dry ice. Well, for every y, I need 1.5 pounds or ounces of root beer. So it says every ratio has an associated rate. Unit rate is another way of interpreting the ratio's proportional constant. The statement below identifies how unit rate defines y and x in a proportional relationship. We've talked about unit rate and unit prices, guys, since 6th grade, right? If I say it's 15 pounds for 2 ounces of laundry detergent, or $15 for 2 ounces of laundry detergent, we've talked about how you can divide 15 by 2 to get your unit rate. You know, remember, unit rate kind of sounds like a unicycle. You want to figure out how much is in one, all right? So usually it's price over item, or a dollar amount over quantity, okay? That's usually how I remember it. So in the previous problem, Carmen was making homemade root beer. It says express the proportional constant as a unit rate. Well, for us, we knew it would be 12 over 8 okay, which would then become, if I'm trying to get how much is in 1, I divide 12 divided by 8, I get 1.5. So then they said, okay, well, what if we change the roles of y and x? Well, if you change the roles of y and x, that means it would be 8 over 12. And if you divide 8 divided by 12, you end up getting 0.6 repeating. So it's really important to remember to always put your y over your x. Okay. We're going to come back to number 7. Okay. Vanessa is mixing formula for her baby. The graph given to the right describes the relationship between the ounces of water. So if you look down here, ounces of water is my y. The scoops of formula, that's your x, right? It says scoops and ounces. Does this graph form a proportional relationship? Yes. And how do I know that? Because it goes through the origin. It goes through 0, 0. And it goes up at the same rate, right? It goes through 0, 0, and it's growing at the same rate. What is the unit rate for this relationship? Show in the graph where you can see that. Well, unit rate is how much is occurring in 1 x. So if I go to the 1 on the x line, we have 3. So it's 3 ounces per 1 scoop, or in 1 scoop. At a different location on the graph, show and explain how you can find the unit rate. Well, I'm just looking for pretty points, right? So here's one right here, there's one here, there's one here. And if I write those points as my y over my x, I have 12 over 4, right? Because it's 4 comma 12. I have 3 comma 9, or 9 over 3. I have 6 over 2. And these all will simplify to the same thing, 3, my unit rate. Write an equation to relate the ounces of water, which was your y, to the scoop of formula. Well, I know that my ounces of water depends on 3 times x. How many scoops does she need to make 9 ounces for her baby? Well, if I come up here to the graph, I want 9 ounces. I know I'll need 3 scoops. I can also plug that into my equation that I wrote here. 9 equals 3x. If I divide both sides by 3, I get x equals 3. All right. I am going to have you guys try number 11 on your own. And then you're going to go ahead and scroll down and do the homework portion of this. Skip number 3. I don't like that problem on the homework. So skip 3. And yeah, go and work on those problems. Come to my office hours if you need help. We'll be working on proportional relationships the next couple days.